Okay, so welcome to this next video in which we are discussing opioid receptors. Okay, so we're currently discussing the effect of the beta-gamma subunit of the heterotrimeric G protein on the voltage-gated calcium channels. Okay, so we spent the previous video discussing the structure of voltage-gated calcium channels, and we saw basically that they are assembled out of these four separate subunits, if you like. You have the gamma subunit here, okay, which is one of these auxiliary subunits, an example of which is this stargazing subunit. Then you have your alpha-1 subunit, which is the main subunit. That's the portion that actually has a pore through which calcium ions can move. Okay, so here's this alpha-1 subunit. Then you have the beta subunit, which is attached to the cytoplasmic aspect of the alpha-1 subunit, so that's down here. And then finally you have this alpha-2 delta subunit, which you can think of as being one subunit because it's actually made by a single gene. Okay, so it's composed of this alpha-2 portion, which is completely extracellular, and then this delta portion, which has a single membrane-spanning alpha helix. Okay, and we've discussed the variability in all of these subunits. Now basically what can happen is the beta-gamma subunit of the heterotrimeric G protein can come and bind to certain voltage-gated calcium channels, and what it can do is inhibit them. Okay, so here comes the beta-gamma subunit, and let's put some colour on this picture. Okay, so let's colour in the beta-gamma subunit in blue and green. So we'll colour in the gamma subunit in green here, the beta subunit in blue, okay, and we'll then colour also in the components of the voltage-gated calcium channel. So we'll colour in the gamma subunit of the voltage-gated calcium channel this time in red. We'll colour in the beta subunit of the voltage-gated calcium channel in orange. We'll colour in the alpha-1 subunit of the voltage-gated calcium channel in turquoise here. And we'll colour in the alpha-2 delta subunit in vivid purple, I think. Okay, right, so here's our picture. So, what this causes is it causes inhibition of the voltage-gated calcium channel. Now, the beta-gamma subunit cannot bind to any old voltage-gated calcium channel. It has to be of a certain type. Okay, so these beta-gamma subunits can bind to PQ-type voltage-gated calcium channels, which, remember, are voltage-gated calcium channels where the alpha-1 subunit is CAV 2.1. So remember, if you had the alpha-1 subunit, which was the CAV 2.1 type alpha-1 subunit, then you were called a PQ-type voltage-gated calcium channel. Basically, this beta-gamma complex here can bind and inhibit PQ-type voltage-gated calcium channels, also N-type voltage-gated calcium channels, which, remember, in N-type voltage-gated calcium channels you have an alpha-1 subunit, which is the CAV 2.2. So I'll just list them out here. This is CAV 2.1, this is CAV 2.2. And then finally they can also do it for L-type voltage-gated calcium channels, which, remember, are any voltage-gated calcium channels where the alpha subunit is any one of the four genes in the CAV1 family of alpha subunits. Okay, so this family here, any one of those four there, and you will be called an L-type voltage-gated calcium channel. So this beta-gamma subunit can actually inhibit quite a few of these voltage-gated calcium channels. And what does it mean to inhibit the voltage-gated calcium channel? Well, it means that even if the electrical potential difference across the membrane depolarizes, which is something that would usually trigger the voltage-gated calcium channel to open and then allow calcium into the cell, with the beta-gamma subunit bound, the voltage change, i.e. the depolarization, will fail to activate the voltage-gated calcium channel, okay, and that will mean that you stop calcium entry through these voltage-gated calcium channels. So, let's now discuss the significance of this for neuronal axon terminals and synaptic transmission, because this is going to be very helpful when we come on to discuss how the opioids actually have an analgesic effect. Okay, so let's just have a little bit of a reminder about how neurotransmission occurs between one neuron and the next. Okay, so here we have an axon terminal here, and then we'll have the dendritic spine, potentially, of the postsynaptic neuron. Okay, so here we go. So here's the presynaptic neuron, and here's the postsynaptic neuron. Okay, so basically, in the presynaptic neuron's axon terminal here, what you will have is synaptic vesicles, which are full up of neurotransmitter, okay, and which are docked at the presynaptic membrane, so they're held right up against the presynaptic membrane. So I'll put little green dots in here to represent the neurotransmitter, okay, like so. Okay, and this zone within the cytoplasm that's close to the presynaptic membrane is known as the active zone. Okay, so basically what happens is when an action potential propagates along the axon, it will make its way into the axon terminal, okay, and it will trigger depolarization of the membrane, electrical potential difference across the membrane at the axon terminal. This will then activate the voltage-gated calcium channels, which for now I'll just draw like so. Okay, so they're being demoted from having their structure drawn out incredibly carefully like this to just being shown like this. So this represents one of these. Okay, now which voltage-gated calcium channels do we actually have here? Well, you have N-type voltage-gated calcium channels and also PQ-type voltage-gated calcium channels within the axon terminal. So these two here, so the alpha-1 subunits of these voltage-gated calcium channels in the axon terminal are either CAV2.1, making it a PQ-type voltage-gated calcium channel, or CAV2.2, making it an N-type voltage-gated calcium channel. Okay, now what will happen is when the depolarization occurs, these PQ-type and N-type voltage-gated calcium channels will open, and then because calcium is so much higher extracellularly than intracellularly, specifically to put some numbers there, the extracellular calcium concentration is 1.5 millimolar. The intracellular calcium concentration is around 100 nanomolar. That is a 15,000-fold gradient. There is absolutely no way in the world that whatever physiological electrical potential difference you have across this membrane, that will stop the movement of calcium into the cell when you open this channel. To put it this way, basically the calcium ions on this side are 15,000 times more concentrated than on this side. So basically the probability that a calcium ion will hit the channel from this side and go through this way is 15,000 times greater than the probability that a calcium ion will hit from this side and go out. Of course, it's slightly more complicated than that because you have to also take into account the electrical potential difference across the membrane, which is influencing the calcium ions' decision as to whether they want to go through the voltage-gated calcium channel. But basically, you're always going to get a net movement into the cell, no matter what the electrical potential difference across this membrane is, at least with physiological limits on the electrical potential difference across the membrane. Okay, so basically, when the voltage-gated calcium channels open, you get calcium coming into the cytoplasm of the axon terminal, and this then triggers the exocytosis of these synaptic vesicles, as they're called, which are these vesicles full of neurotransmitter. Okay, so the synaptic vesicles will fuse with the presynaptic membrane and release their neurotransmitter into this space in between the presynaptic and postsynaptic neuron, which is called the synaptic cleft here. And then it will diffuse across the synaptic cleft and act on receptors on the postsynaptic neuron. Okay, right. So, what's the effect of stimulating the axon terminal with opioids, basically? So, often the location of opioid receptors is on the membrane of the presynaptic nerve terminal. Okay, so let me draw a bigger picture here. So if we have our presynaptic axon terminal again, then we'll basically have an opioid receptor here. Okay, and generally it's the mu opioid receptor, but we'll keep it nice and general and just say it's an opioid receptor. And basically, if some ligand comes and binds to this opioid receptor, okay, so in comes the ligand, what we know is this opioid receptor will then interact with the heterotrimeric GIG protein. It will produce the two active subunits, the alpha I GTP subunit and also the beta gamma subunit. So here alpha I GTP and also the beta gamma subunit. Now we're not too interested in the fact that the alpha I GTP will go on to inhibit adenylyl cyclases. We're very interested in what the beta gamma subunit does. So we know two things that this does. It causes hyperpolarization of the membrane, okay, by opening those G protein gated potassium channels, okay, which are members of the inwardly rectifying potassium channel family, and it also inhibits the voltage gated calcium channels. Specifically, it does inhibit these N-type and PQ-type voltage gated calcium channels. We're not too interested in L-type with regards to axon terminals because you don't really have L-type voltage gated calcium channels in axon terminals. Okay, now what are the two effects of this? Well, basically, if you hyperpolarize the membrane of the axon terminal, is the action potential that is propagating from the axon going to find it easy to propagate into the axon terminal? Well, the answer is no. Remember how an action potential occurring at one portion of the membrane passes to the next portion of membrane, okay? So let's just have a little revision of this. So let's say this portion of membrane, which I'm highlighting in orange, is undergoing an action potential, okay? So what has happened is that sodium has come in from the extracellular fluid and has depolarized the electrical potential difference across the membrane, and in an action potential it can go up to plus 40 millivolts, meaning that the electrical potential intracellularly is 40 millivolts higher than the electrical potential extracellularly. The way this propagates to the next portion of membrane is some of this sodium will diffuse over here and cause depolarization of the electrical potential difference across this portion of membrane. So let's draw a little graph for this. So let's plot the electrical potential difference across this portion of membrane here. So it might start off at something like negative 65 millivolts. Okay, now in order to fire an action potential, what you need to do is bring it up to around negative 40 millivolts. Okay, that's the threshold potential for the activation of the voltage gated sodium channel. So let me put a voltage gated sodium channel here. So in order to activate the voltage gated sodium channels, which I'll show in blue here, you need to bring the electrical potential difference across the membrane up to around negative 40 millivolts. That is what this sodium that's diffusing in from this other portion of membrane is going to do. Okay, when you bring in positive charge here, it will increase the electrical potential of the intracellular compartment, and that means that the electrical potential difference from extracellular to intracellular is going to become less negative, because remember what this means is that the intracellular compartment has an electrical potential 65 millivolts lower than the extracellular compartment. Okay, now if we're bringing in positive charge here, we are raising the electrical potential of this intracellular compartment. We're not changing the electrical potential of the extracellular compartment. So when we ask how much lower is the electrical potential of the intracellular compartment compared to the extracellular compartment, the answer is it's going to be less negative, basically, okay, because we brought this one up. So the amount you're going to have to go down in going from here to here is going to be reduced because we brought this one's electrical potential up. Okay, so basically what will happen is usually this will depolarize the electrical potential difference across the membrane to threshold potential negative 40 millivolts, and then what will happen is these voltage gated sodium channels will open. They will allow sodium to move from the extracellular fluid into the intracellular fluid, and this will cause a very rapid depolarization, okay, because we are moving positive charge out of the extracellular compartment, we're bringing it into the intracellular compartment, okay, so we're raising raising the electrical potential of the intracellular compartment, reducing the electrical potential of the extracellular compartment. Therefore, when we ask how much does the electrical potential change when we move from extracellular to intracellular, it actually starts to go into the positive regions where the electrical potential intracellularly is actually greater than the electrical potential extracellularly. So you go up generally to around plus 40 millivolts, where if you move from extracellular to intracellular, you will go up in electrical potential by around 40 millivolts. Okay, right. Then what will happen is the voltage-gated sodium channels will inactivate, okay, so they will close, and also the voltage-gated potassium channels will open, okay. Now, voltage-gated potassium channels were actually activated at negative 40 millivolts as well. So both the voltage-gated sodium channels and the voltage-gated potassium channels, which I'll show here in turquoise, they were both activated at this threshold potential down here. The difference is that the voltage-gated sodium channels activate extremely rapidly and then they inactivate, okay? Whereas the voltage-gated potassium channels take much longer to activate, so they're only just about to open when the sodium channels start closing, okay? So these are opening at this point, and what they will do is they'll allow potassium to move out of the cell, and of course you're now moving positive charge out of the cell. You're taking positive charge away from the intracellular compartment, moving it into the extracellular compartment. Therefore, you're raising the electrical potential of the extracellular compartment and reducing the electrical potential of the intracellular compartment, and that will mean that the electrical potential difference glides back down, okay, and then it will and then these voltage-gated potassium channels will close, and then it will go back to equilibrium, okay, to resting potential. Okay, so basically, if we have hyperpolarized the membrane of the axon terminal here, okay, by opening these G-protein gated potassium channels, is the action potential going to find it easy to propagate from the axon into the axon terminal? The answer is no, because now the electrical potential might be much lower maybe. Maybe we've taken it down to negative 70 millivolts. Okay, now in order to induce an action potential here, you're going to have to bring in a greater amount of sodium ions from this neighboring portion of membrane. So let's say this portion of membrane is now this orange portion here, which is providing the initial sodium ions which depolarize the electrical potential difference across this portion of membrane. Okay, now if this portion of the membrane is hyperpolarized, then the amount of sodium that you're going to have to provide in order to bring the electrical potential difference across the membrane up to negative 40 millivolts is going to be greater, because we're already at a hyperpolarized level, so you're going to have to go up a greater amount, okay, and potentially the action potential will not be able to provide enough sodium to actually trigger an action potential in here. So you might get a state where even though there are action potentials coming down the axon, they just cannot propagate into the axon terminal, and therefore are not going to trigger the release of neurotransmitter by the axon terminal. In addition to that, even if the action potential does propagate in, you've inactivated those of the voltage-gated calcium channels, so that even if the membrane of the axon terminal does undergo an action potential and depolarizes, it won't activate the voltage-gated calcium channels, so you won't get the calcium signal coming into the cytoplasm, and it's that calcium signal that causes the release of neurotransmitter. So both of these things lead to the reduction in the release of neurotransmitter by the axon terminal, even if action potentials are propagating down the axon. So they reduce the amount of neurotransmitter that axon terminals will release. Okay? So this is one of the key locations where you find opioid receptors, on the presynaptic nerve terminals, and then when you stimulate the opioid receptors with opioids, they will block basically that presynaptic axon terminal from being able to release neurotransmitter, even if the axon is screaming at the axon terminal to release neurotransmitter. Okay, right. So we now want to discuss the actual ligands for opioid receptors. So we haven't actually discussed yet ligands for opioid receptors. We've discussed the pathways that they activate, but we haven't actually discussed what activates them in the first place. Okay, so let's firstly begin with the actual endogenous ligands. Okay, so we're going to start with the endogenous opioids. Okay, and some people will refer to the endogenous opioids as endorphins. Okay, so that name is for endogenous, and then the orphins is for morphines. So endorphins, which is short for endogenous morphines. Okay, right. So, let's have a look at the different endogenous opioids then, or the different endorphins. So we're not going to go through absolutely all of them, but I'll give you some examples. Okay, some very important examples. So one that actually the general public has generally heard of, which is beta endorphin. Okay, this is a ligand for mu opioid receptors. It's a agonist for kappa opioid receptors and delta opioid receptors. So it activates all of the opioid receptors other than the opioid receptor-like one. Another example of endogenous opioids is leucine enkephalin. Okay, and you put a leu for leucine and then enkephalin. Okay, which is another example of an endorphin. Okay, then we also have methionine enkephalin, which we'll abbreviate to met enkephalin. Okay, so there's 3 examples now of endogenous opioids. And then one final example is dynorphin. Okay, right, and again it's got the orphin suffix, okay, to imply that it's an endorphin. Right, okay, so all 4 of these are all agonists for the mu opioid receptor, for the kappa opioid receptor, and also for the delta opioid receptor. Okay, so we haven't actually yet seen endogenous agonist for the opioid receptor-like one. So I will now give you the main endogenous agonist for the opioid receptor-like one. And this is a protein called orphanin PQ, or it's sometimes also called nociceptin, okay? So orphanin PQ / nociceptin. And sometimes another name that people use for the opioid receptor-like one is to call it the orphanin PQ / nociceptin receptor, basically. Okay, so this is the endogenous ligand then for the opioid receptor-like one, the ORL1. So these are the endogenous opioids that we have within our body that stimulate these receptors. So we don't just have receptors for morphine, basically. They are receptors with endogenous ligands, and morphine just happens to be an exogenous agonist for those receptors. Okay, so we'll call it there for this video and then discuss more exogenous ligands, other examples of exogenous ligands, and we'll come back to morphine and heroin in the next video.